Can anybody tell me what is the value of D that you can get? We still have to find this lambda.
It's 1.65.
Okay, it is 1.65 into 10 to the power okay minus 10 meters. So this is your value of D. But because we have to find the maximum wavelength. So what do you mean by maximum wavelength? For maximum wavelength, you should have a maximum value of your sine theta, right? So the maximum value of sine theta is possible at what angle? Sine theta is maximum as 1, right? And that 1 is possible when you have theta equal to 90 degree. Okay, so we can write this equation, which is 2d sine of theta, as 2 multiplied by the value of your d, which is 1.65 into 10 to the power of minus 10 is equal to the wavelength. Since we are considering it can be a n integer of a wavelength, we can consider n at to be a first order reflection. So you can calculate you can calculate the wavelength. So what is the wavelength? Can anybody calculate what is the wavelength?
D. Option D.
Option D.
C.
Option D or option C? Because we have to calculate it in nanometers, right? So what is the right option? The right option is C, which is 0.332 nanometers. Is it okay? So I think we can move to next question.
Excuse me, ma'am. I have a question, ma'am.
Yes.
Ma'am, would you explain the meaning of A?
The A is actually the lattice parameter. What we say that for example, if this is a unit cell, the distance between your nearest neighbors is the A. So for example, if this is if it is a simple cubic, for example, in this case, then the nearest neighbor is this corner and this corner, right? So these two are the nearest neighboring. So you can say the distance between these two atoms, which is from their centers, that will be A if it is a simple cubic. But because this structure is not a simple cubic structure, it will have some FCC atoms in between. The distance between these two corners will be pushed. So these two will not be the nearest neighbor, but this and this face centered atom will be the nearest neighbor. So that is actually the distance between the two from the centers of the two nearest neighbors. Depending on what kind of a crystal structure you have, you can have different like nearest neighbors. For a simple cubic, it is simply the atoms at their edges, while as for FCC, it will be the atom which is at the corner and at the face. The distance between them is the lattice parameter. Okay. So next question we have. The next question says that silicon carbide is an example of. So you have also read about various types of bondings such as ionic, covalent, metallic. So so silicon carbide is which type of a bonding? Is it ionic, covalent, metallic, or van der Waals?
Covalent.
Right, it is a covalent bonding because we know that there is a difference in these bonding is based on their how the electrons are distributed. Right, for an ionic bonding, the electrons are kind of they are one atom is contributing the atom electrons and the other atom takes the complete electrons. While as in a covalent bonding, we have the electrons that are being shared between the two atoms or two species. So based on that, we can say that silicon carbide is a covalent bonding. The electrons are shared between the two. Okay. Now we have another question that says which plane among the given planes of a BCC crystal will give a diffraction peak. So you understand that based on what kind of a crystal structure you will have a different planes or indices that will be visible in your XRT. So you know that according to Bragg's law, only the planes that satisfy the Bragg's law will be able to be seen in an X-ray diffraction pattern. So for a PCC crystal, what are the reflections that you are allowing, which are allowed according to the Bragg's law, so that we can have a diffraction peak. So you know, for a BCC, we always know that H. It is a general rule which says that H plus K plus L is even, right? So based on this rule, you have to identify which of these planes will be among the planes for the PCC crystal. So first is 100. So the addition of the three is 1, right? So not it is not a BCC plane, right? Then we have 1 1 1 and the addition gives 3, which is odd. Again, it is not a plane that will be present in a BCC diffraction pattern. But when it comes to 112, so you have the addition as 4, which is an even number. So you can have a diffraction pattern for a BCC that will show a plane of 112. Similarly, you will have a diffraction pattern which will have a plane 220 also. So 220 is also right. Okay, so based on your this general rule which says that H plus K plus L is even for a PCC crystal, you can identify which are the allowed reflections and what are the planes that you can identify in your XRD. Is it clear? So next question, we have next question that says it's again based on your diffraction pattern. It says that you have a in an X-ray diffraction pattern a peak appears at 44.65 degree. So you have an angle at which the peak is appearing. Okay, this is actually an angle between your when you are doing an XRD analysis, the angle is actually angle between your source and your deductor. So this is the angle that is between the two, represented by 2 theta here. That is the position which you know. So in your XRD pattern, this is your 2 theta, which is the position at your of your satisfying the Bragg's condition, and this is your intensity. So it is saying that in an X-ray diffraction pattern, you obtain a peak at somewhere around here, which is 44.65 degree, and it corresponds to 101 plane. Okay. So you have to find out the lattice parameter of the crystal. That means you have to find the A for the crystal. So if you are given an unknown sample and you identify its plane and position, you can also determine the lattice parameter of the crystal. You can know if the for example, if you have a natural crystal which is having a lattice parameter of say A, but after a certain treatment or certain microstructural changes, the lattice parameter has changed from A plus some delta X. So the change in the lattice parameter can also be identified using the XRD pattern, and that can give you an indication that the material has undergone certain mechanical changes, changes, and because of that it will have a different properties. So again, here we'll be using Bragg's law. So according to Bragg's law, we know 2d sine of theta is equal to n of lambda, right? So you know here the peak will appear at 44.68. So remember, this is the 2 theta angle. This is not a theta angle but 2 theta. So 2 theta is given by 44.68. 22.65. Okay, so you can calculate theta. I think it will be around 22 point something like this. You have also been given a plane which is 101. So you know that d is equal to the lattice parameter divided by your h square plus k square plus l square, that will be under root of 2. So using these two equations you can try to find the value of your lattice parameter, which is a. So you can write it like this: 2 multiplied by, using this value in this equation, 2 lattice parameter divided by under root of 2, and then sine of theta, that is sine of 22.3 is equal to your lambda, which is the wavelength of your source that you're using. See, in your previous question you had to find the wavelength that you have to utilize to find a certain plane. Here you are already given the copper. Copper is the source from where you are emitting a wavelength of certain which is 1.54 angstroms. So using this wavelength you are able to determine a diffraction pattern for a component or for a metal with a lattice parameter of A. So here the wavelength is 1.54 multiplied by 10 to the power minus 10 in meters. So can you find the value of A? What is the value of A? Or you can put it in angstroms. So that you can get the value of A also in angstroms. Okay, can anybody tell me what is the value of A?
2.86 times.
Okay, so we have 2.86 angstroms. Okay, so this is your answer. Is it clear? I think we can go to next question. The next question says that what are the Miller indices of a plane in a cubic unit cell having plane intercepts at A, 2B and 3C. So you are given a plane in a cubic unit cell. So you have three intercepts. You have A, which is A, B and C, and the intercepts are 1, 2 and 3. So you have to identify what are the Miller indices. So how we calculate the Miller indices? We take the intercepts, we take their reciprocals one by one, and then we find the common factors. So we have 6 as a common factor. We can write 6, 3 and 2. So this is the Miller indice for a plane that was having intercepts of 1, 2 and 3. So the answer here will be this, B. Is it clear?
Yes.
Okay, so I want you to do the next question that says that index the highlighted plane in the hexagonal unit cell. So you have to sorry, you have to index the plane which is highlighted. The highlight plane is the front plane of this hexagonal unit cell. So you have to identify the plane. So you know that in hexagonal unit cell you always have three axes. which are at 160 degree to one another. So you have A1, A2, A3, and the third x and the fourth axis is perpendicular to that. So first we will see the intercepts in all of these four directions, right? Say on A1 we have an intercept of this plane as 1. Okay, so we can write 1. And for A2 we do not have any intercept along A2 direction, right? Because it is parallel to the A2 direction, so there is no intercept around A2 direction, so we can write 0. We can and in the third direction, which is A3, the plane is cutting it in the negative direction, so you have to extend it in this direction, so you have minus A3. So you have minus 1 intercept in this direction, in third direction. And along C direction there is again no intercept because it is parallel to the C axis, so it will be 0. So our plane, we can index it as 1 0 1 bar 0. So this is our plane, and the right option will be D. Is it clear?
Ma'am, what are the angles between these three axes A1, A2, A3? Is it 120 degrees?
No, the like for between each axis it is around, like for A1 and A3 it will be 60 degree, and the third will be like perpendicular to that. If you see A1 and A3, these are 60-degree angles because it is a hexagon.
Okay.
So you have 101 bar 0 as a plane. So next I want you to do the next question. So you have to say that in a cubic lattice which direction lies in the plane 2 to 1. So you are given a plane 2 to 1 and you have to say which of these direction will be present in this plane. Remember always that whenever we are given a direction in a plane, uh, it is always that these two are in the like they have the same direction. So if they have the same direction, their dot products will be 0. So you have to identify which among these direction will have a dot product with this plane which is equal to 0. So you can say that direction is contained in the plane. So always whenever you are given a question that says if this direction is part of a plane or it is contained in that plane, you have to refer to their dot product, and sorry, if the dot product comes out to be 0, then that direction will be contained in the plane. So you can try this question and say what is the right answer out of these options.
Option A.
Option A. So we can find the dot product between the two. So that will be 2 plus 2, and this is minus 4 bar. So minus 4 and 1. So you have minus 4. So the overall dot product will be 0. So option A is the right option. So direction 114 bar will be present in the plane of 2 to 1. Okay. Next question. You can do this question which says that we have three directions. One is this B, A, B, and C. So you have to index all the directions. So starting with, say for example, A, you have, the starting point for the A is this point. So you can take the origin for this point here instead of where we generally take it at the center of the at the origin of the cube. You can also take the origin from here for this particular direction. So you can say that in this direction along x-axis it is going along negative x-axis, so it will have minus 1 or bar 1 direction. Along y-axis it is there is no change. Along z-axis there is no change, so you have 0 and 0 along uh, y and z axes. So the direction A will be referred to as 1 bar 0 0. This will be the direction for your A because you have chosen the origin from this point. Okay, now you have to see what is the direction. You have to index direction B and direction C. You can tell me what is the direction B. For direction B, the origin is this. So remember, it is going from origin and then it is ending at your front face. It is ending at the corner of your front face of your cube. So you can say that it has traversed some distance outside of this cube. So it will be, say for example, 1, and after that it has traveled in this direction, and then it has traveled some y direction also. That will be 1. It has then traveled along z axis also, which is +1, so 1. So this is your direction, 1 1 1. That is your B direction. Now can anybody tell me what is the C direction? For C we have to choose this as origin, and then you have to tell me the direction. Can anybody tell me what is the direction for C? How we write or how we index the direction for C? Can anybody tell me what is the direction for C? So that will be 1 by 3 of 1, because V is 0, so that will be 1 by 3. And for this W we will have that is as 1, and we have to see also T. So the T is given by minus of capital U plus capital V. So that is equal to minus of minus 2 by 3 plus 1 by 3, and it is equal to 1 by 3. So now what are the coordinates we have? We have this, which is minus 2 by 3, V, which is 1 by 3, T, which is 1 by 3 again, and W, which is 1. So taking for this we can take the common factors, and we can say it is minus 2 1 1 and 3. I think so that is the conversion for this. Is it clear? Now can somebody find the directions for this queue? First in three indices, then in four indices. So first for this queue, we would like to have indices in. Maybe we can erase it, and then we can do for queue. Can anybody tell me what is the indices for q, direction q? First in three coordinate and then four coordinate.
It is -1 0 0.
Okay, so let's see. It is along a1 direction but in a negative, so it will be -1. But there is no translation in a2 direction, a3 direction, or c, so everything will be 0. So -1 0 0. So this is your for a three coordinate. Now can you convert it to a four coordinate and tell me what is the answer? For a four coordinate system, we have to find u. That will be -2/3, right? The capital V, that will be equal to 1/3 of, I think, minus u, that will be +1. So that will be 1/3. We have w, which is equal to 0, and we have t, that is equal to minus of -2/3 plus 1/3. So we have 1/3 minus 1/3, that will be plus 1/3 overall. So we have now coordinates -2/3, 1/3, 1/3, and 0, right? So you can have -2, 1, 1, 0. This is your direction for q. Is it clear? Anybody can tell me the direction for r, the in three coordinate, then you can find the four coordinate yourself. So we can just do the three coordinate for r first. Remember, it is the this prism, this on the left hand side, this prism. So you can consider it to be a cube, and then we have the direction starting from edge of this cube to the front. This is just in the front face. There is no it is not going to the back face. So remember, it is only in a single face of this cube. So it will be traveling 1 along a1, and there will be no translation around a2 and a3, and there will be one translation around c. So what will be the direction for r?
1 0 1.
So the direction for r will be 1 0 and 1. So then you can convert it to a four coordinate system for conversion to UVWT form. Okay, so you can do that. So we can move to next question. Now we have this question that says index the planes in hexagonal unit cell. So you have a now planes. So we were just indexing directions. Now we have to index the planes. Okay. So you are given two planes P and Q. So can anybody tell me what is the indexing for plane P? So you have to find the intercepts of each plane. For P plane, you have intercept at A1. So you have to find the intercept for A1, A2, A3, and C. So can you tell what is the intercept for A1? For A1, the plane is intercepting at a distance of 1, right? It is cutting it at a 1. So you can write 1. For A2, it is running parallel to the A2 direction. See, the plane is parallel to A2 direction. So there is no intercept along the A2 direction. Okay. So you can write, say for example, infinity, and then for A3, again we have a parallel, it is parallel to A3, so it is not having any intercept along no, it is having an intercept along A3. So yes,
Minus
yes,
1.
yes, it is having an intercept along A3 because this is positive A3 and this is negative A3. So it is having -1 along A3, and for C along Z direction it is having an intercept at 1 because it is cutting it. The plane is going from a front face of a prism to a back face of a prism. If you see, this is actually a cube. This is just the same as a cube. This one which is highlighted. So the plane is going from a front face to the back face, right? So it is cutting it at 1. So you can say 1. So overall the plane is 1, 0, 1 bar, 1. So this is the plane for P. Now, can you tell me what is the indexing for plane Q? For plane Q, it is actually parallel to all directions. It is just having one intercept along the C, and it is parallel to all directions A1, A2, A3. So, what will be the intercepts?
0001.
So, this is your plane for a plane Q, the indexing for a plane Q. Is it clear? So, next, so we have this plane which is maybe I can just say, so you have now this plane is starting from this edge to this edge, so you have to index the plane. Remember, whenever you are indexing a plane in a cubic cell, you should not choose an origin that contains the plane. That means you cannot choose this as an origin because it is containing the plane, right? So you have to choose the origin which does not contain the plane. So you have to identify the plane in this question. So can anybody tell me what is the plane? You have to choose origin very carefully in this question. And you are given a coordinate system. Sometimes the coordinate systems will be given to you, and then you can choose to index according to that coordinate system. So you are given x, y, and z. So this is your x, this is your y, sorry, this is your z, and this is your y. Okay. Say for example, if you are choosing it this as an origin, this point is your origin. So what do you say for an x? Do we have an x intercept? We do not have an x-intercept in this because the plane is parallel to the x-axis, right? So there is no intercept along x-axis, so we can write infinity. For y, we have a intercept at 1 unit distance, right? So you can write 1. And for a z-axis, we have intercept at the negative of a z, so you can write 1 bar. So the plane will be 0, 1, 1 bar, and that is option C. Is it clear?
Ma'am, I have a question.
Yes.
Um, can we have a family of planes with negative intercepts? That means having bars.
I didn't get it. Can you please repeat?
Suppose I am creating a family of planes.
Yes.
Okay. So what example we have seen in these and in the videos of what we have. Only positive inter. I have seen the planes with only positive intercepts.
No, we have a negative intercept here. See, Z is negative here.
My question is that can we create a family of planes with negative intercepts? Is it necessary to have family with only positive intercepts?
Well, no, the intercepts will change depending, like for example, if you have a taking the same cube, say for example, so you have this plane and you have this plane. Depending on where you take the origin, you will have an intercept as negative. So, but both are belonging to the same plane. So, I think that will not make a difference.
But suppose in this question the answer is 0, 1, 1 bar.
Yes.
I have said to write one more plane which is a part of the same family.
Mm-hmm.
How would I write that? That is my question.
If the plane
Suppose
is a
yeah, I want to write one of the members which belongs to this family, 0, 1, 1 bar. So
okay,
can I write 0, 1 bar 1? Will it be part of the same family?
0, 1 by 1, yes, it will be a part of same family.
Thank you.
So we have next question that says identify the lattice plane of Miller indices 130. So you're given a Miller indice 130 and you have to identify which among the three planes it corresponds to. So first remember Miller indices are given. So once the Miller indices are given, we have to convert them to their reciprocals to find the intercepts. So this will be 1. So here you have to do the reverse of what you were doing earlier. First we were trying to find intercepts and then take the reciprocals and then find the Miller indices. But here we are given the Miller indices, so we have to find their reciprocals. So this is 1 by 1, this will be 1 by 3, and this is 1 by 0, which is infinity, right? So can you tell what is the which among the three is the right plane? That means we have an intercept on x-axis which is 1, we have an intercept on y-axis which is 1 by 3, and then we have an intercept on z-axis which is infinity, that is parallel. So the first thing is it is parallel to the z-axis, right? This is fixed, that is the plane will be parallel to z-axis. And then it is saying on x-axis we will have an intercept of 1, and y-axis we will have an intercept of 1 by 3.
Option C.
Right, option C is right because you are having an intercept of 1 by 3. You have uh, along x-axis you have intercept of 1, taking this as an origin because now the plane is not contained in that origin. You see the origin is beyond the plane. So from origin you can take x as 1, and because for y we are giving an intercept of 1 by 3, so it will come around to this point, and then it is parallel to the z-axis, so you can draw a parallel and then you can found this plane. So this Miller indice corresponds to this plane, which is plane C. Okay, so we have next question that says the Miller indice of plane PQRS are. So you have to identify the Miller indices for the PQRS.
Ma'am, suppose in a problem, the principal directions are not mentioned. So what is the default axis we should choose as the x, y, and z? Like in the same question,
Mm-hmm.
nothing has been mentioned about the axis.
Yes.
Which one is x, which one is y. So
So
what is the default rule in this case?
normally we take it as like this: x, this is your y, and this is your z. So you can identify this PQRS now based on the Miller indices. Can anybody tell me what is the answer for this? The plane is parallel to z-axis, right? And you have to choose a origin which does not contain the plane. So you cannot choose this as origin. This is not the right origin. So you cannot choose this as origin. Now you have to say what is the Miller indices for the plane. So if you choose, say, for example, this as an origin, so the intercepts will be -1, right? And for a y, it will be +1, and it is parallel to z-axis, so it will be -1, 0, -1, 1, 0. I think the option has some errors. It will be 1 bar is 1, 0. Is it clear? You have to carefully choose your origins because that will determine your correct Miller indices. The plane will not contain the origin. Always, whenever we are indexing a plane, the origin should not be containing in the plane. Then only we can correct it. Then we can index it correctly. Is it clear? Now you have to identify the plane here. This is your plane. You are giving x direction. You are given y direction, z direction. So you have to identify what is the Miller indices for this plane.
From my side, the answer should be 201.
201. So how have we done that? We have chosen this as origin.
102, sorry, 102. Sorry, 102.
102. So um, for this question, right?
Last question.
So what is the intercept on your x-axis?
I have taken half.
Yes, 1/2. And y?
Infinite.
Yes, because it is parallel to y. And for z, we have 1, right? So we have 1. First, we will take the, yes, I think you can take it 102, right? Okay, so now we have another question, that is the last question for today. So it is based on the same concepts of how we have a crystal structure and how the lattice parameters are related. So we are given a question which says that we have a germanium. Germanium, you know, it is a semiconductor. It is used in semiconductor industries. So we have a sorry, germanium, which is having a crystal structure similar to silicon. Okay, so it is having a lattice constant of 5.64 angstroms, okay, which is converted to 0.564 nanometers. So you have to find the atomic density for this structure. Always remember that you have to first know the atom. What is atomic density? Atomic density is nothing. It is actually given by the formula. It is number of atoms per centimeter cube. So that means centimeter cube is actually the volume. So you always define density with respect to a volume. So atomic density is equal to the number of atoms you have for a particular species, and divided by the centimeter cube. It is actually the volume, number of atoms per unit volume. So what is the volume here? We are talking about here the volume of unit cell. In terms of crystal structures, whenever we are talking about volume of unit cell, number of atoms per unit of the volume cell, we can find the atomic density. So you have to first find what are the number of atoms in this structure. So you have this structure which is having a crystal structure similar to silicon. So only the atoms will be the atoms that will be contributing to the crystal structure. We can calculate that. So when you have a unit cell, and if you have atoms at the corner positions like these, you have 8 corners for a unit cell, right? And these corner positions are actually being shared by different unit cell. There is unit cell here also, there is a unit cell present here, there is a unit cell present here, there is a unit cell present at the bottom. So this particular unit cell is surrounded by unit cells on all directions, on sides of it, on front of it, and behind it. So all of these are containing the unit cells. So this atom is actually being shared by 8 unit cells at a time. So these corner atoms always contribute 1 by 8th to the unit cell only, right? So the contribution of this atom to this unit cell is only 1 by 8, and because we have 8 atoms, so we can multiply it by 8. So the corner atoms are contributing 1 atom to the unit cell whenever we are talking about say for example a face centered cubic cell. And then also there are atoms at the faces of the unit cell. So this is the face. There are 6 faces, the 2 at the like front, back, and then other 4 sides of a cube. So there are 6 faces, and each face is shared between 2 unit cells. So this atom which is on this face is shared with this unit cell and the unit cell which is present here. So this is shared between 2 unit cells always. So it will contribute only half of its atom to this unit cell, and the rest half is contributed to the other unit cell. But how many number of atoms we have? We have 6. 1, 2, 3, 4, 5, and 6. So we have 6 face centered atoms. So overall the number of atoms that are belonging to this unit cell are actually 1 plus this 3. So we are having 4 atoms of a unit of the this contributing to this unit cell. So if you have find the atomic density now, so the density of the atoms will be number of atoms, which is say for example if it is having a face centered cubics, so it is 4 divided by the volume of the unit cell. So what is the volume of the unit cell? Because we know it is a cubic structure, and we know the one side of the dimension, which is lattice parameter. So that is 5.64. So we can write volume as a cube. So that will give your atomic density, right? So you can calculate what is the atomic density for this.
Excuse me, ma'am.
Yes.
Ma'am, in this problem, how we um, um, took volume of unit cell equal to A cube, because earlier you said A is the lattice parameter,
Mm-hmm.
which is the distance between the corner atom with its nearest neighboring atom.
Mm-hmm.
As we see in this diagram, if we use the formula for unit cell equal to A cube,
Mm-hmm.
A is not the side of this cube. A is the lattice parameter which is different from the side of this cube.
Mm-hmm.
This formula, is it okay to apply A being the A as a side of this cube, A into A cube, like we have seen in the mathematics?
Yeah.
Because A should be the arm of this cube, distance between the two corner atoms.
No.
A, what is given is the lattice constant, which is the distance between the corner point with the face center point.
Right, right. So here we only like whenever we take say for example for a unit for this unit cell, how we will take the volume. The volume will depend on its lattice parameters, right? So if we are taking the closest neighbor will be this and this, the face centered atom, and then from the face centered atom to this atom. So the closest distance will be from the corner and the face atom, but overall we will take their a is not the distance between this edge and this edge. It is actually just a distance between the two closest neighboring atoms. So we can
So,
take it.
ma'am, how can we take this distance as the edge of the cube? Because this distance will be different from what we have seen in the formula for a volume of a cube.
Yeah, because volume of this cube will be the volume will be defined by your like what is the edge to edge length for in all three directions, right? So if we take in one direction, for example, if you are taking this direction, so the a cube will be actually the distance between these two atoms. So that will be a. That is your closest neighboring distance.
When we are finding the formula for a volume of the unit cell,
Yes.
okay, so it is in a cubic shape. Okay, finding the value of the volume of a cube is simply the multiplication of its edges.
Yes.
Edges means the distance between the two corner points,
Hmm.
not between the face center point with the corner point. That is my objection.
Okay. Okay. So, okay, I might have to check it. I am not really sure about that, but I will check for this particular problem if there is any issue with that. Because I think the volume of a unit cell we always take is as a cube of your like what is the lattice parameter of that unit cell. So maybe we can check for
But
this.
in mathematics, we calculate the volume of a cube by taking the edge, cube of the edge.
Right, right.
Edge here is the distance between the two corner points, not between the corner and the face center point, as we have pointed out.
Yeah, but when you put it in a closed packing system, you will not have these two atoms together. You will have them far apart. So you will have this something like this, and this is your face centered atom. This is your corner atom. This is your corner atom, and then there will be this face centered atom in between them.
But that concept is okay when we are defining the edges constant only.
Yes,
Here I am talking about the finding the volume of the unit cell.
yes, yes, yes. Maybe we
Maybe
can
there may be some.
go through it again. I'll let you know. I'll try to check it, and then I will let you know. Yeah. So I think this was the last question that we had for today. So if anybody has any doubt, you can write an email also. So I'll share my email ID here. So you can write